What if we could discover life-saving drugs or highly efficient green catalysts in a matter of days instead of decades? Well, let's start right off the bat by asking this massive question, because it gets right to the heart of why modern chemistry is in desperate need of a total overhaul. I mean, for centuries, chemistry has basically been a painstaking process of trial, error, and immense patience. But what if the lab of the future doesn't actually rely on human patience at all?
Welcome to this explainer. Today, we're diving deep into how artificial intelligence is fundamentally rewriting the rules of chemical science. We are literally witnessing a molecular revolution right now, moving entirely away from slow, heuristic guesswork and stepping into this wild new era of intelligent, data-driven innovation. So here is our game plan for today. First, the bottleneck. Then, AI methodologies. Next, networked molecules, followed by accelerating discovery. After that, we'll hit autonomous synthesis and finally wrap up with the quantum future. All right, part one, the bottleneck. So, traditional chemistry relies so heavily on human trial and error. Finding just a single viable drug candidate can take anywhere from 10 to 15 years and cost billions of dollars. And why? Mostly because humans have to manually synthesize and test thousands of compounds, essentially crossing our fingers and hoping for the best. But AI-driven chemistry totally flips the script. It's predictive. It rapidly generates and screens viable candidates virtually, way before a single test tube is ever touched. The whole transition is basically about ditching manual catalyst screening that's based on basic, heuristic guesswork. Instead, we're handing the reins directly over to deep learning and computational modeling. This lets us optimize yield and structure computationally, which is a massive leap from educated guessing to high-dimensional mathematical certainty. Moving on to part two, AI methodologies. Now, AI isn't just one magic wand. It's a really diverse, highly specialized toolkit. You've got foundational machine learning like random forest, predicting molecular properties like toxicity or solubility based on past data. Then deep learning handles all the complex 3D structure analysis and nonlinear correlations. We also use natural language processing, or NLP, which acts like this tireless research assistant, instantly extracting reaction data from millions of dense scientific papers. And finally, generative models like GANs and variational autoencoders don't just analyze data. They actually dream up entirely novel molecules optimized for specific, customized tasks. That brings us to section 3, networked molecules. To actually give the AI its eyes, so to speak, we use something called graph neural networks, or GNNs. GNNs are super fascinating because they treat a molecule exactly like a social network. Think about it. In a social network, you have users and you have their friendships. Well, in a GNN, the atoms are the users or nodes, and the chemical bonds are their friendships or edges. This setup allows the neural network to seamlessly process the 3D geometry and connectivity of a molecule, predicting exactly how it's going to behave with astonishing accuracy. Section 4, accelerating discovery. To really appreciate the speed we're talking about here, you have to look at the computational cost required to simulate molecular behavior. The traditional gold standard for quantum accuracy, which is known as coupled cluster theory, has this crippling computational cost that scales to the power of 7. It's just too heavy for large systems. Density functional theory improves this to a qubit cost, which is better. But machine learning interatomic potentials, they are the real game changers here. They scale linearly, meaning they give us near quantum accuracy without us hitting a massive computational wall. 100,000, that's the number to remember. By utilizing these AI neural network potentials, we can actually run virtual catalyst testing and molecular dynamic simulations an astonishing 100,000 times faster than traditional quantum chemical calculations. Seriously, what used to take months of supercomputer time can now literally be done in an afternoon. It's mind-blowing. All right, section 5, autonomous synthesis. Okay, but discovering a brilliant new molecule in a computer simulation is really only half the battle, right? We still have to physically create it in the real world. And this is where AI tools for retrosynthesis come into play. Imagine an AI acting like a master architect. It integrates reaction prediction, mechanistic insight, and optimization to map out the exact synthetic routes needed to build a molecule from scratch. Programs like Cynthia and these advanced generative transformers predict the most cost-effective, high-yield, and environmentally benign step-by-step disconnections. So when you take that AI retrosynthesis and combine it with robotic lab hardware, you get what's called an autonomous agent, a self-driving lab.
The AI is the brain. It generates the hypothesis, screens the candidates virtually, and then directs robotic platforms to physically execute the chemical reactions. It learns from the outcome, refines its next experiment, and just keeps going 24/7. No coffee breaks, no weekends off, just a pure, continuous discovery. And finally, Section 6, the quantum future. Now, you might be wondering, what happens when we eventually hit the limits of classical computing? How do we achieve the exact fundamental descriptions of quantum mechanics for these massive, incredibly complex biological proteins and materials that our current computers just can't handle? Well, the next massive horizon is integrating AI with quantum computing. Quantum-enhanced machine learning promises to model these highly complex electron interactions with absolutely unparalleled precision. Now, to be clear, full practical quantum advantage is realistically still 1 to 3 decades away. But early pilot projects are already showing us that this synergy is going to completely revolutionize areas like homogeneous catalyst discovery for industrial processes, like nitrogen fixation. Ultimately, merging computational chemistry with AI is about securing our everyday future. These aren't just abstract concepts. These innovations will directly impact everything from the cost of the medicine in your bathroom cabinet to the energy grid powering your home. By optimizing catalysts for energy and pharmaceuticals, we're designing smart materials to convert renewable biomass into valuable products with maximum efficiency and absolutely zero waste. I love this quote because it beautifully summarizes the journey we've just been on. Collectively, AI and computational chemistry herald a new era in catalytic organic synthesis, transitioning from empirical discovery to intelligent, data-driven innovation. We are officially leaving behind that old era of slow, heuristic guesswork. We've stepped into a completely new, data-driven reality where the boundaries of what we can synthesize are only limited by the data we can provide to our models. So, I'm going to leave you with this provocative thought to chew on. As these autonomous, self-driving labs become the new standard, relentlessly operating day and night, what impossible, world-changing problems will we finally be able to solve next? Think about it. Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you next time.